Hey everybody, in this video I'm going to show you how to convert a radiance measurement into a reflectance measurement. So radiance is the amount of, or the energy density recorded at the sensor, and reflectance is the fraction or percentage of light or energy reflected off of the surface, okay? So we're going to convert something we measure at the sensor, that is radiance, into this kind of intrinsic property of the surface, that is the reflectance. So to motivate this, I'll give one example. Imagine, for example, that we wanted to estimate the concentration of suspended sediment in water. This picture is from Long Island Sound in 2011, about a week and a half after Hurricane Irene. This is Long Island here. This is Connecticut. This is the Connecticut River dumping sediment into Long Island Sound. Suppose you wanted to know the concentration of that sediment plume and estimate a sediment flux. One way to do that would be to compare reflectance spectra that you extract from an image with reflectance spectra of turbid water that you measured in the lab. So here's an example of reflectance spectra for different turbidities or different concentrations of suspended sediment. Okay, and you can see they're different. So if you could actually quantitatively compare those with spectra you extract from the image, you could estimate suspended sediment concentration. Now, to do that, you can't do that with radiance, right? Because the illumination conditions between the lab and the image are going to be different. So by definition, you'd get really different radiance measurements between a lab sensor and a satellite sensor. But the reflectance, that unitless reflectance, should be the same. So that's an example of why we might want to convert radiance in a satellite image into reflectance. And I pretty much just said this, but computing to reflectance allows us to compare images with lab spectra, but it also is important because it can allow us to compare spectra from images that are collected at different times of day or different seasons, right? When perhaps the solar angle or the total solar illumination is different. Maybe it's cloudy. So reflectance, in theory, gets rid of these different illumination conditions. Likewise, it lets us compare images from different sensors that might be calibrated differently or might have measured radiance differently. So again, just to define this, what is reflectance? It's the percent of incoming radiation that is reflected back off the surface. Often we express it as a fraction. It's important to distinguish here quickly between total reflectance, which would imply we're considering all wavelengths of light at once, versus this term spectral reflectance, which is essentially the reflectance within some certain range of wavelength. So you might say, what's the spectral reflectance in the blue wavelength, right? Which would be what percentage of blue light is reflected off the surface. Okay, so this is going to be a bit of a tedious video, so please stick with me. What we're going to do is we're going to set up this simple diagram, and we're going to start with the assertion that reflectance equals L over E, okay? Where L is the outgoing radiance and E is the incident irradiance, okay? So we're looking to estimate E first and then L. We're going to take a ratio of them to get this term, the reflectance, down here. And we're going to do this really, I just said basically in two steps. First, we'll estimate E. We're going to correct for solar illumination properties and correct for atmospheric transmissivity. And then in the second part, we're going to estimate L, or outgoing radiance, by converting dN to radiance, again correcting for the outgoing atmospheric transmissivity, subtracting path radiance, and then correcting for Lambertian scattering. So let's get started. Let's start by estimating E, okay? And that's going to start with an estimate of this value, E naught, up at the surface. So E, the first correction we're going to make to get to E is the sun elevation correction, okay? And this is the simple idea that when the sun is high in the sky, okay, maybe up here, it puts down a higher energy density onto land. In other words, the photons from the sun fall basically over a smaller area and you get a higher energy density. So therefore, the actual energy from the sun that's hitting a horizontal surface falls off as a cosine of the sun angle here, okay? So when this angle is 0, the sun is straight overhead, okay, and cosine of 0 is 1. By the time the sun's way down here, this angle is 90, cosine of 90 is 0. So this first correction we're going to make, we're going to take E naught, which is the average irradiance at the top of the atmosphere. That's essentially a constant, 1362 watts per meter squared, and we're going to multiply it by the cosine of the solar angle measured from the vertical. Okay, that's going to give us our first pass at E. The next correction we need to make is to correct for the Earth-Sun distance. This is a very small correction, but it's required because Earth's orbit around the sun is not circular, it's an ellipse. So at certain times of year, Earth is much further or somewhat further from the sun, and that has a small effect on the amount of incoming insolation. So to add this, we are going to take what we had before and divide by d squared, where d is the Earth-Sun distance in astronomical units. That ranges from about 0.983 to 1.016. Okay, so those two corrections were step 1a. Now step 1b, the final part of estimating incident irradiance, is to correct for atmospheric transmissivity. That is literally the fraction of energy consumed as the sun's rays or the photons go through the atmosphere from the sun to the surface, okay? This is a fraction from 0 to 1. 1 would imply 100% of the energy is transmitted. This is difficult to know. This value actually changes by day, depending on the weather, of course, cloudy versus sunny. So this is something, in some cases, we'll just ignore this and assume that it's 1. In other cases, we'll actually go look it up, and there's different atmospheric models you can use to estimate transmissivity. And there's also a variety of more sophisticated techniques as well. But anyway, in this example, we're just going to add it in as a factor. So we're going to take what we had before, and we're going to multiply it by this fractional transmissivity t. It's going to reduce it a little bit. Okay, so congratulations, you've now finished part 1. You have the formula for estimating the incident irradiance, also known as half of the reflectance, the denominator of reflectance. If you're in my class, I'm going to ask you now to open up the Excel worksheet that is linked on the Canvas page, and that worksheet's going to have you follow along, making your own calculations as we go through this video. So you're going to want to stop the video as needed from here on out and work the calculations by hand, and ultimately you're going to compute an example reflectance. Okay, so with that in mind, let's jump on now to part 2, where we're going to actually estimate the other half of reflectance, the outgoing radiance, or L. Okay, and we're going to do this in 4 steps. It's a little more complicated. So our estimate of L is going to be based on what we actually measure at the satellite, also known as the measured radiance. So we're going to call that L tot, or L total, total radiance measured. And our first step, or step 2a, is going to be converting a digital number to radiance, right? If this thing arrives we just downloaded a Landsat image, it's going to be encoded as a digital number. You need to convert it to radiance. We have a whole video about this regarding radiometric resolution, which I urge you to check out. But very briefly, you'll do that conversion with a radiometric response function in which you have this linear relationship where the measured radiance equals the gain times the digital number plus an offset b, where the, in this case, especially for folks in my class, it's quite common that we can always estimate the gain as L max minus L min divided by dN max minus dN min. So that is the slope of this line. And in this case, and it's quite common for Landsat, the offset B is just going to be equal to L min. So if you need to get some of these parameters, let's say you're actually working with real data, you're always going to find these in the metadata. And for example, with a Landsat image, in the Landsat metadata, you'll find actually a specific L min and L max for each band. And then here, instead of using the term DN, they're using QCal max. So they're basically saying band 1, the digital numbers for band 1 go from 1 to 255. So that's where you can find some of that information. If you're doing the worksheet, that's some of this is given to you in the worksheet. Okay, great. So we got this number L tot in radiance. Okay, congratulations. Next thing to do is to account now for outgoing transmissivity, right? This light has to go back through the atmosphere to get back to the satellite. So we're going to assume that transmissivity is the same, right? It's the same transmissivity that it came down. It also went back through in an instant. So it's the same deal. It's a fraction. And we can now express this by saying the measured radiance, L tot, is equal to L, whatever came off of the surface, the outgoing radiance, times that transmissivity T. And for all the next steps, I'm going to show you this math kind of in two forms. I'm going to show it to you as a definition for L tot, and then also I'm going to show you the same equation solved for L. So this equation solved for L is just L tot divided by transmissivity. Okay, good. So that was step 2b. We corrected for the transmissivity. So now, the next thing we need to think about is called path radiance. And this is the idea that not all of the light that's arriving at the sensor actually reflected off the ground. Much of that light reflected off the ground, but some of it actually may have reflected off of the clouds, reflected off the atmosphere, or it may actually have been emitted by the atmosphere as well. So we have some fraction of the photons or some amount of energy that didn't come from the ground, and that's called the path radiance. And so essentially we can think of that as now the total measured radiance is equal to whatever came off the ground, L, adjusted downward by the transmissivity, plus the path radiance, okay? So if we solve this for L, our best estimate of L now would be whatever we measured, L total, minus the path radiance, divided by the transmissivity. So I'll urge you, don't forget to work on your worksheet as needed as we go along. So you might be wondering, how do we get this path radiance number? Where does that come from? Again, there's a few ways we can do this. Some of them involve quite complex atmospheric models, but the simplest way is lovely and simple. It's called dark object subtraction. And before I get to that, I just want to show you an example of path radiance, okay? So here's an image, a satellite image. Notice these wispy clouds in the forefront, right? Those white clouds, what is that? That is literally photons or energy that was reflected off the clouds and not off the ground. So that's a problem, right? So to correct that, or if you do a dark object subtraction, you can actually remove those clouds and get a cleaner image. So mathematically, how do we do dark object subtraction? What we do is we look at the radiance values of all the pixels in the image, and we ask which pixel is lowest. And we then subtract the lowest pixel value from all of the other pixels, okay? And the logic here is that the dimmest or darkest pixel, if you assume that that actually has a reflectivity of 0, that it's actually not reflecting any energy at all, and that any energy reflected by any energy measured for that darkest pixel must be entirely from path radiance. Okay, that's kind of the assumption you make when you do dark object subtraction. Another assumption you make, of course, is that the path radiance is the same for all pixels, right? You're basically guessing at the path radiance using the darkest pixel, and then you're subtracting that from all the pixels, assuming it's the same for all of them. So that is a major limitation of dark object subtraction. So if you know that you have clouds, for example, then you typically would want to use a much more sophisticated way to estimate path radiance. A DOS works best for pretty clean images, but it is simple. Okay, so hopefully you've now done your dark object subtraction on your worksheet. And good news, we are in the final step here. The final step is to correct for scattering of light from the surface. Everything we've done so far has kind of assumed that all the energy that hit the surface, also, whatever was not absorbed, so whatever was reflected, kind of went directly back to the sensor. But that's not actually true, unfortunately. We know that from a previous video that you can check out on Lambertian Scattering, we know that most surfaces on the ground are quite complex scatterers. They may scatter light in all different directions, okay? Which means the majority of light actually doesn't make it back to the detector. So if we assume that our surface is indeed a Lambertian reflector and that scattering is equal in all directions, in other words, the incoming photons are scattered uniformly in all possible directions, then the energy measured at the sensor is the total that was reflected divided by the solid angle into which the light was scattered. So what is a solid angle? You know what a 2D angle is. I guess I think of a solid angle as being a three-dimensional angle. It's as if you were defining an angle on the surface of an overlying sphere, basically, or an overlying hemisphere. And the solid angle defined by that hemisphere or sphere is given by the area of the sphere, in this case 4 pi r squared, divided by the radius squared. So when you do out that math, essentially for one single hemisphere is a solid angle of 2 pi. So this brings us to our final step, where we now have to acknowledge that the total radiance measured at the sensor was whatever came off of L times adjusted downward by the transmissivity, and also now divided by 2 pi to account for the fact that only one part in 2 pi made it back to the sensor, and then plus the path radiance. So if we solve this out for L, this is now essentially our final equation to describe L as a function of the measured total radiance at the sensor. So congratulations, we now know both L and E, right? And recall that reflectivity was just equal to L over E. It was the outgoing radiance divided by the incoming incident irradiance. So we can stack up both of our equations here that we developed, one over the other, and we can bring in then simplify that to this kind of final equation for reflectivity. So in summary, we computed reflectance in 2 steps. First, we estimated the incoming surface irradiance, E, using solar angle, Earth-Sun distance, and also transmissivity. That was the denominator. Then we estimated the numerator L as first by estimating L total as a radiance or converting it to radiance, adjusting for outgoing transmissivity, subtracting path radiance, and adjusting by 2 pi to correct for Lambertian scattering. Thanks, everybody. Take notes and finish your worksheet.